Okay, what we're looking at here is a neuromuscular junction, and that is where the axon terminal of the neuron is shown in yellow. So this is the axon terminal. It's the end of this axon branch that is swollen. It's swollen and it contains synaptic vesicles, and those synaptic vesicles contain acetylcholine, those little green molecules inside. So the space, so here's your muscle fiber, and at the neuromuscular junction, the sarcolemma is folded, and we call those junctional folds. So where the sarcolemma is folded, in other words, the junctional folds or the motor end plate, it's also called the motor end plate, there's going to be acetylcholine receptors. That's these little blue, they're gated ion gates basically, because when the acetylcholine binds to the receptors, those gates open and sodium ions are going to enter. But right now we're just getting the terminology. So we have the axon terminal is this swollen end of the axon, synaptic vesicles which contain acetylcholine, and then the synaptic cleft is the space between the axon terminal and the junctional folds of the nerve fiber, the sarcolemma of the nerve fiber. And okay, that's good. All right, so that's our terminology that we need. So there's 4 things that must happen for the skeletal muscle to contract. You must have a nerve impulse that leads to events at the neuromuscular junction, which leads to the acetylcholine release from the axon terminal. So the events at the neuromuscular junction, then muscle fiber excitation, and that's going to have to do with an electrical event at the sarcolemma of the muscle fiber. And then excitation, contraction, coupling. That means the electrical event is coupled to the mechanical event, the contraction of the muscle fiber. And then the part that we call cross-bridge cycling, which describes the contraction of the muscle. So these are the steps, the sequence of all of the events that lead to contraction, and they're broken up into those 4 components. So we'll start with the events at the neuromuscular junction. You can see a picture here. So the first thing is an action potential is fired down the axon. So just kind of picture an action potential or nerve impulse arriving, coming from the beginning of the axon, either in the brain or the spinal cord, and arriving here at the axon terminal of at the neuromuscular junction. Okay, so an action potential arrives, a nerve impulse arrives, and then the motor neuron's axon terminal releases acetylcholine by a process called exocytosis. These vesicles are going to fuse with the plasma membrane of the axon terminal, and then they're going to open up and release that acetylcholine into the synaptic cleft. Then the acetylcholine will bind to the receptors on the junctional folds of the sarcolemma. You will also hear that referred to as the motor end plate of the sarcolemma, which is the plasma membrane of the muscle fiber. So you see the little green molecules binding to their receptors. And that is going to cause, this is our last step of the first part, events at the neuromuscular junction. Our last step is that the binding of acetylcholine to those receptors is going to open these gates. It's going to open the gates of these ion channels. Sodium is going to enter. Sodium ions, which have a positive charge, are going to enter into the muscle fiber. And that is going to change the voltage or the potential at the sarcolemma. That voltage was negative 70 millivolts, and it's going to change to a more positive voltage. Okay, so it's going to change. It's going to go toward negative 55. And we call that depolarization, when the potential, the resting potential, the negative 70, becomes less negative and more positive. All right, then we are going to have the muscle fiber excitation. That depolarization, once it reaches a value we call threshold, which is negative 55 millivolts. So once enough sodium ions have entered to depolarize that membrane, that sarcolemma, to the threshold value of negative 55, then an action potential will be generated right there at the sarcolemma. And once that action potential is generated, it's going to travel all the way down the sarcolemma, down the T tubules, which are a little bit further down, but it'll travel down the T tubules to the interior of the muscle fiber. Okay, so the for the excitation contraction coupling part, an action potential in the sarcolemma travels down the T tubules. So that that potential or that voltage is changing all along the plasma membrane or the sarcolemma of the muscle fiber, and then it's changing all the way down the T tubules, and it's going to a more positive value because what's causing that action potential are positive ions, positively charged sodium ions. Now, once the action potential reaches the T tubules and then it reaches the sarcoplasmic reticulum, or the portion of the sarcoplasmic reticulum called the terminal cistern, then that is going to release calcium. And those calcium ions are going to, this is going to be the contraction part, they're going to bind to the molecule troponin, and that will shift the tropomyosin out of the way so that those active sites on actin are uncovered. I'll show you a picture of that in a minute of what that looks like when it happens. But calcium is going to lead to the uncovering of the binding sites on actin. Then the myosin heads are going to bind to the actin and form cross bridges. And the last step is called cross-bridge cycling, and that is the events of the actual muscle contraction. So we'll look at that. Excuse me. So we covered the events at the neuromuscular junction already. We covered the release of acetylcholine. We said that an action potential arrives at the axon terminal. Calcium ions are actually, they enter into the axon terminal through these voltage gated channels. So actually calcium plays two roles in muscle contractions. It begins in the neuron, and then calcium is going to play another role in the muscle fiber. But because the action potential has arrived at the axon terminal, calcium is now going to move into the axon terminal and trigger those synaptic vesicles to release acetylcholine into the synaptic cleft. The acetylcholine will bind to its receptors, and that then, if you blow up those chemically gated ion channels here, after the acetylcholine binds to its receptor, those ion channels open up and sodium, which is positively charged, moves in to the muscle fiber through the sarcolemma, the junctional folds of the sarcolemma. So when sodium comes in, it makes the potential or the voltage across the sarcolemma more positive. It was at a negative 70 millivolts, and it's going to go into a more positive direction. Now, this video, events at the neuromuscular junction, is slide 63, and it's a good one to watch, but we're also going to do some animation tutorials, interactive tutorials through interactive physiology. We're going to do that Thursday in class. And I've also put them in your concept application part assignment in mastering. So let's see, a homeostatic imbalance example is the one they're giving here is of the disease called myasthenia gravis. Myasthenia gravis is characterized by drooping eyelids, upper eyelids, difficulty swallowing and talking, and just general muscle weakness. And it involves a shortage of acetylcholine receptors because a person's own antibodies attack their acetylcholine receptors. So that means it's most likely an autoimmune disorder. So it's a shortage of those acetylcholine receptors. So a lower number of those receptors means a lower number of a less depolarization at that motor end plate. So less depolarization of the sarcolemma here, and that's going to mean less likely that an action potential will be generated. Okay, so the only thing here I want to mention is the depolarization of the sarcolemma occurs because sodium diffuses into the sarcolemma. After the acetylcholine binds, sodium comes into the sarcolemma and the sarcolemma becomes less negative, or another way to say that is it becomes more positive. And that is what we call depolarization. It's when that potential or voltage across the plasma membrane or sarcolemma becomes less negative. And that's because of sodium coming in. Okay, now, if this depolarization reaches threshold, which is typically, so the resting potential or voltage is negative 70 millivolts. Threshold is typically around negative 55 millivolts. So when enough sodium comes in through those chemically gated channels, through those acetylcholine channels, then that voltage changes to threshold, and when threshold is reached, an action potential is generated. An action potential is going to result in more sodium channels opening, but these are voltage gated. These sodium channels are opening in response to that threshold value. Once that threshold voltage or potential is reached, then those voltage gated channels open. So more channels for sodium ions are opening, more sodium is coming in, and a lot more sodium, a whole lot more sodium. So this is the action potential part. So an action potential or electrical impulse is triggered that's going to spread or travel all the way across the sarcolemma into the T-tubules. Okay, so it's like the action potential is like a wave of depolarization. So the first thing that happens is in the action potential is that voltage-gated sodium channels open in response to the voltage change, the depolarization to threshold. Okay. Now, once that voltage or potential reaches positive 30, it's around positive 30 millivolts, then those sodium gates are going to close. No more sodium is going to come in, and potassium gates are going to open, and potassium is going to leave. Since potassium also has a positive charge, that's going to make the voltage go back into a more negative direction, and we call that repolarization. So depolarization is when the negative voltage or potential becomes more positive, and repolarization is when that positive potential across the membrane becomes more negative and goes back to its original resting value. Okay, so depolarization in the notes is when the potential becomes more positive. The potential or voltage and potential mean the same thing. So when that voltage across the sarcolemma becomes more positive and leads to an action potential, that's depolarization. Repolarization is restoring the resting conditions, which means that the membrane potential is going to become more negative again. So sodium ions coming into the muscle fiber coming into the sarcolemma are going to cause depolarization. Potassium leaving, so we say potassium efflux, causes repolarization. There is a refractory period, and during that time, the muscle fiber cannot be stimulated again. Another action potential cannot be generated. That is called the refractory period. Okay, so here's a graph that shows you the voltage changes across the membrane. Now, I said -70. They're using -90 here. It's probably a difference in textbooks and just information changes over time. But so it's a very really negative voltage or membrane potential at rest. And then once acetylcholine binds to its receptors on the sarcolemma, sodium channels open up and sodium starts coming in. Well, once the sodium has led to a depolarization to the value that we call threshold, and I don't know where that is in this graph because all you see is -90 and 0. But somewhere around here, threshold is reached, and now you're going to see rapid depolarization. This is when your action potential is generated. So once that threshold is reached, the voltage-gated sodium channels in the sarcolemma will open, and a whole lot more sodium will rush in to the sarcolemma. That's depolarization and action potential. So the action potential is going to lead to a voltage change all the way to +30. So much sodium comes in that the voltage or potential moves all the way to +30. Then the sodium channels will close, the potassium channels will open, and you will start seeing potassium ions leave. That will lead to more negative. Okay, and that is called repolarization. And eventually the potassium channels will close. Okay, so excitation, contraction, coupling are the events that connect the action potential along the sarcolemma. That's the excitation part, is the action potential traveling along the sarcolemma and the T-tubules. And that is coupled to the attachment of the myosin to the actin. And that's the contraction part. Then we're going to have the events of the cross-bridge cycling. It's called cross-bridge cycling. Okay, so this picture shows you the very last part of excitation, contraction, coupling. You can see an actin filament and a myosin filament, and you can see the myosin filament has these two heads on it, and the actin filaments have these little dark spots that are covered by tropomyosin. This strand is called tropomyosin. They are the binding sites. So myosin, when a contraction happens, myosin must bind to those binding sites on actin. Well, that is triggered by the release of calcium. Once the action potential reaches the terminal cisterns, so it travels down the T-tubules and reaches the terminal cisterns, they release calcium, and calcium attaches to troponin. And it causes the shape of troponin to change, and it moves the tropomyosin out of the way, exposing those binding sites, and now myosin can form a cross bridge with actin. So that is the excitation, contraction, coupling part. And there's a video of that. This is slide 77. And then we have cross-bridge cycling. Which I'm just going to point one thing out. Cross-bridge cycling involves, after the myosin heads bind to the actin, to the binding sites on actin, then they perform a power stroke. They pull on the actin, okay? So they perform a power stroke, and that's going to release the ADP and phosphate that was attached to the myosin. So in other words, it requires energy. And then ATP is now going to come in and bind to the myosin so that it can detach. So ATP will bind to myosin and it will detach from the actin. And the contraction is over.